Welcome back to real time digital signal processing course. So, last class we were looking into LMS algorithm. So, we will see that how we are going to derive this one in today's class. So, we have started with the adaptive filters, why do we need it and what are the applications it is going to be used. One of the application we saw it as our hearing buds and then other things. So, today we will see that how we can derive our adaptive filter, that is basically least mean square LMS algorithm. So, we discussed about the method of steepest descent in the last class. So, that is it is a iterative or recursive process technique that starts from some arbitrary initial weight vector W0 and it is going to descend to the bottom of the bowl what we said. So, by moving on the error surface in the direction of negative gradient estimated at that point. So, you will be estimating it and then going down in the thing. So, for L is equal to 2, so this is the error surface what we have got it and this is the error contours in concentric circles what we will be getting at. And then how we are going to calculate, we said we will be deriving this shortly. So, that is the weight update, that is future weight update n plus 1 is going to be done with the current weight minus mu is our step size basically, as you can see in the error surface how you will be coming down, and then the gradient vector eta of n. So, that is what we call it as gradient of the mean square error function with respect to our weight function. So, negative sign indicates that the weight vector is updated in the negative gradient direction. So, we will take up an example and see how we will be coming with work on the steepest descent algorithm. So, the function given, we need to obtain the vector that would give us the absolute minimum what we are looking at. So, y of C1 comma C2, so which is given capital C1 square plus C2 squared. So, it is obvious that C1 is equal to C2 is equal to 0 give us the minimum basically. So, this is the quadratic ball, C1 is in this direction, C2. So, we know that this is what we are expecting. So, in the ball how we will be traversing and coming down what we will see. In practical applications we may not reach 0. So, as an example, so assume that C1 is equal to 5 and C2 is equal to 7 in the beginning, and we are going to select the constant mu. If it is too big, we miss the minimum. If it is too small, it would take us a lot of time to hit the minimum. So, in this case we will select mu is equal to 0.1. The gradient vector is defined by this, which is dy by dc1 and then dy by dc2. So, which is equal to 2c1 and then 2c2 what it is going to be. So, our iterative equation is what we are going to have, it is C1 and C2 of n plus 1 is given as C1 C2 n minus 0.2 multiplied by our gradient vector. So, which is nothing but C1 C2 this thing n minus what we have is, because we have 2 C1 and 2 C2. So, if we take it out, so it is going to be C1 C2 n into 0.1 what we are going to get the thing. So, when we substitute this, 1 minus 0.1 will be our 0.9. So, this is 0.2 divided by what you are going to have, it is 2. So, that is the reason why what you will be getting it as 0.1. So, now what we are going to substitute is iteration first what we have C1 C2 is 5 and then 7 is been given, and in the second iteration. So, C1 C2 according to this equation substitute C1 C2 and then solve the thing 0.9 C1 C2 what we are going to have it. So, the next iteration, so by multiplying C1 C2, so you will be getting it 0.9 times 5 is going to be 4.5 and this becomes 6.3 and then continue this in the iteration 3 4.5 into 0.9. So, this is what we will be getting it and C2 is this value. So, at iteration 60 as you can see that the value has come down to 0.01. So, you will be seeing that initial guess what you have taken the thing C1 C2 and then you are traversing down the thing. So, here it is going to be 0.01 0.013. So, as we can see the vector C1 C2 converges to the value which would yield the function minimum and the speed of this convergence depends on our step size. So, in this case we had taken it as 0.1 is our step size mu basically, that is what we have assumed in this case. So, now what is the thing is going to happen. So, how to calculate the mu or how to arrive at the least mean square algorithm what it is shown here. So, in many practical application, so statistics of our desired signal d of n and x of n are going to be unknown, that is input signal. So, the method of the steepest descent cannot be used directly since it assumes the mean square error is available to compute the gradient vector. So, then what happens, you will be seeing the LMS algorithm developed by Widrow. So, you can go to the net and then see he is the one who designed our least mean square algorithm, uses the instantaneous squared error E squared of n to estimate the mean square error. So, which is given by eta of n is you will be putting it as E squared of n. So, the gradient estimate is partial derivative of this cost function with respect to the weight vector. Then what happens to our gradient which is going to be given by 2 times our gradient of error vector into error vector what we will be putting it E squared of n. So, then since we know that our error function is given by d of n minus y of n and y of n substituted with w transpose of n into x of n, what is substituted, then what we have is our gradient of E of n is given by when you take the gradient of it which results in minus x of n. So, the gradient estimate becomes as it is given by minus 2 into x of n into E of n and the weight vector w of n plus 1 is going to be w of n plus mu x of n into E of n. So, what is from where you got you have substituted the gradient thing with respect to this I think you can derive the thing. So, the constant mu what we will be putting it into our update vector here. Okay. So, then how we are going to calculate our LMS algorithm. So, the diagram on the right side it shows that it has an input and then we have the weight vector here and then y of n is our output and this is the desired signal. The difference between the two will give us the error which is fed to our LMS algorithm which will modify the weights based on our input x of n. So, this is what the figure shows and we will write down the steps which are going to be followed in the algorithm calculation or weight calculation and then the output calculation and error. So, we are going to determine the values of L is the order of the filter, mu is the weight vector and w of 0 is the initial values for our weight vector. So, that is what it gives the thing, this is the step size and w0 is the initial weight vector at time n is equal to 0. So, it is very important to determine these parameters values properly in order to achieve the best performance of the LMS algorithm. So, we will compute the adaptive filter output as y of n is equal to r w L of n into x of n. So, we know that it is a W transpose of n into the vector form into x of n. So, which is nothing but it is L is equal to 0 to L minus 1 W L of n into x of n minus L, and we will be computing the error signal as E of n is given by, in the second step, D of n minus y of n. So, we have calculated y of n, and weight vector initially we have assumed as 0, and then we will start with it, and then whatever the desired signal what we have given minus the output will be the error. Initially, as we know that y of n may be 0, so it will be error will be very high, because we have assumed the weight to be 0 and then x of n. So, error will be high, and then you will be seeing once it starts coming down, it will be adapting to weights are adjusted. This is how we will be calculating our W L of n plus 1 is going to be given by W L of n plus mu into x of n minus L into E of n. So, where L is the length of our filter, which is going to vary from 0 to capital L minus 1. So, hence you will be seeing that number of computations what it is going to have in calculating the LMS algorithm is 2L additions and 2L plus 1 multiplications what we are supposed to do to get the output. So, that is what the computation complexity of the LMS algorithm. So, coming to the thing how our graph is going to converge. So, we will see the thing unknown channel of second order what we have chosen the thing, and then this graph is going to illustrate, that is what you have the initial guess here, and then this is our E1 and then C1 and then C2 what we have selected initially as we said. So, then what happens? So, it will be traversing depending on our mu, will be traversing in this way in the concentric circle, and try to, we are supposed to get to 0. So, as we know that it is in practical situations, it is not possible to achieve this. So, we could only decrease the error below a desired minimum, so that we will be able to work on it. So, there are different modified LMS algorithms to reduce our computation time. What are the things? There are 3 types to improve the computation. One is the sign error LMS algorithm. Here as you can see, W of n plus 1 is given as W of n plus mu into x of n, and you will be taking the sign of the error n. So, sign data LMS algorithm, the other one, sign of E of n is given as 1 or minus 1. So, if error is greater than or equal to 0, we make it 1. If it is less than 0, it is going to be minus 1. So, that it is either a negative of it or positive. So, that we are avoiding the multiplication by error of n in this case. So, the sign the other one is sign LMS algorithm. Here it is based on the sign error, the other one is on the sign on the data what you are going to have it. Then in this case what happens, sign of x of n, so that you are reducing your computation. The other one is sign LMS algorithm. So, this algorithm requires no multiplication and designed for mostly VLSI or ASIC implementation to save multiplications. So, in adaptive differential pulse code modulation, that is ADPCM uses for this algorithm for speech compression. So, I think we will be taking the speech coding little later. So, we will see why we need the compression there. Okay. So, how it is going to work for a complex signals, that is LMS algorithm. We have seen the DFT and other things for the complex signals. Here also we have to see that how it is going to work from least mean square. Applications dealing with complex signals, the frequency domain adaptive filtering require complex operations to maintain their phase relationships in this case, and then the complex adaptive filter uses, that is complex vector x of n and complex coefficients w of n. So, then x of n is real part of x of n plus j times imaginary part of n, and w n of is also represented both in real and then imaginary parts in this way. Then we know that complex output signal y of n is computed as y of n is w transpose of n into x of n, what we have it. So, where all multiplications, additions are going to be complex operations. So, the complex LMS algorithm adapts the real and then imaginary parts of w of n simultaneously as in this fashion, w of n plus mu e of n into x conjugate of n. So, adaptive channel equalizers use x conjugate of n as x real of n minus j x imaginary of n. So, we will see these applications little later. So, we have to see the performance analysis of our LMS algorithm. As we know that IR filter, we consider the stability constraints. So, we have to see, first one is the stability, next is how we are going to have the convergence rate, and then we will be seeing that x is mean square error and how it is going to have the finite word length effects on our algorithm. Just like any our linear filter, we have to see in the adaptive filter also. So, how these parameters are going to affect us. So, the first one is the stability constraint. So, that is 0 less than or mu, which is less than, we have taken it as 2 by lambda max is the one. Lambda max is the largest eigenvalue of the autocorrelation matrix R. So, as we have will be seeing in the lab that we selected if mu is equal to 1, how our output was getting affected. So, this is the way, otherwise arbitrarily we can choose the thing and then what is the thing is going to happen. So, we have looked in the lab. So, here what is should be the mu value, which should be less than 2 times lambda max. Lambda max is our autocorrelation eigenvalue of our autocorrelation matrix R. So, we know that computing our autocorrelation matrix and finding out the eigenvalue is compute intensive, and then how we are going to take the thing, that is lambda L or the eigenvalues of our matrix R. In that the maximum value what we will be taking it and then divide 2 by that value. So, the other way of doing selecting our mu is from the stability point of view. So, we can have a mu 2 divided by L into Px. L is the length of the filter and then Px is we know that it is the autocorrelation function of the first this thing input signal, which is nothing but expected value of x squared of n is the power of r x of n. So, this equation provides two important principles for determining the value of mu from these two constraints. What is it? The upper bound of the step size mu is inversely proportional to the filter length here. Thus, a smaller mu must be used for a higher order filter and vice versa. Since the step size is inversely proportional to the input signal power, a larger mu can be used for low power signal and vice versa. The other way is more effective technique is to normalize the step size mu with respect to power p such that the convergence rate of the algorithm is independent of mu. That is what one has to look at it. So, now coming with the convergence speed, continuing with the thing. So, each adaptive mode has its own time constant for convergence. So, which is going to be determined by the step size mu as we know, and the eigenvalue associated with lambda L with that mode. Thus, the time needed for convergence is clearly limited by the slowest mode caused by the minimum eigenvalue and can be approximated as time to calculate minimum mean square error is approximated as 1 by mu into lambda minimum. So, lambda minimum is the minimum eigenvalue of the matrix R what we are considering. This is the maximum time what it is going to take place. If we choose a lambda max, then we know that time to compute this is going to be lesser. So, we say because our time tau mean square error is inversely proportional to the step size mu, using a smaller mu will result in a larger time basically, that is slower convergence, and when our tau max is very large, only a small mu can satisfy the stability constraint. So, these are the things one has to consider when you are selecting your mu. So, if lambda minimum is very small, the time constant can be very large, resulting in very slow convergence here also. The slowest convergence occurs when using the smallest step size mu is equal to 1 by lambda max. So, you will be seeing that both of them are inversely proportional to our mu step size and then lambda minimum. So, both will be contributing to the slow computation time for our adaptive filter. So, then what is it? We say that our mean square error time is given by less than or equal to lambda max by lambda min, and which is by substituting lambda min we can do that, which is less than or equal to lambda max divided by minimum is approximated as maximum x of omega, that is magnitude of x of omega whole square divided by minimum of x of omega whole squared. So, how is this? We know that x of omega is the dt of t of x of n. So, we will be seeing that eigenvalue spread can be efficiently approximated by the spectral dynamic range in this case. So, we can see how the computation is going to be more. So, now other way of is how we can control our mean square error by using x's mean square error. So, which is eta x's is given as L into px into eta minimum. So, we know that. So, the approximation shows that the x's mean square is directly proportional to our mu, and then the use of larger step size mu is going to result in a faster convergence rate at the cost of degraded steady state performance by producing more noise. This is what we saw in the lab, or you can yourself see that by making a mu a larger step size only it will be giving you noise. So, therefore, there is a design trade off between the x's mean square error and the convergence speed when choosing the value of mu. So, now how we can normalize this mu basically, or our step function. So, then later on what it was developed is normalized LMS algorithm. So, which is given by this equation, that is 0 is less than mu, which is less than n by r px. So, as it L is the length of our this thing filter, and px is the power what we have to calculate. So, you will be seeing that it will take more time than LMS algorithm. Then your update function for w of n plus 1 is given, selecting this mu with our x of n and then a of n. So, you will be seeing that where mu of n is the time varying step size one has to calculate, it is not pre-computed, as and when you are depending on your input power, you will be calculating your step size, and then it can be normalized by the filter length and signal power as mu of n is given as alpha constant divided by L into Px of n plus some constant C, where our Px of n is the estimate of the power of x of n at time n. So, and alpha will be taking the value between 0 and 2, which is a constant, and C is very small constant. So, that we are not going to have, when this becomes 0, division by 0 is avoided by this constant. So, very small, so that this is not going to get affected, or using a very large step state for a very weak signal at time n. One has to note that Px of n can be estimated recursively. So, NLMS algorithm will take little time compared to our LMS. So, how we are going to choose this Px of 0 as the best a priori estimate of our input signal power. So, a software constant may be required to ensure that mu of n is bounded if it is very small when the signal is going to be absent. So, that divide by 0 is avoided. So, how we are going to do this one? Software implementation is shown in with few steps, that is we will be assigning our mu E of n is assigned as mu into E of n. For L is equal to 0, L less than our length of the filter. So, you will be continuing it. This is the W of L is calculated with respect to mu into whatever you have calculate mu E n into x of L. So, that you will be you need not have to do this multiplication inside every time, which is a consume, you know that within the loop if you do the multiplication it will be adding on. Instead of that, you compute and keep it outside and then use it for you will be reducing the multiplication. So, you can see that the updation can be done once in a sampling period, what we will be doing it, instead of every sample to reduce the computation and to take care of the pipelining delays. So, the delayed LMS algorithm, which is expressed as W n plus 1 is nothing but W of n plus mu into E of n minus delta. This is the delay what you are going to give it, and even the input signal is going to be delayed by delta x of n minus delta. So, if you assume delta is equal to 1, then E of n minus 1, that is previous sample what you will be taking it, previous error what you will consider, and then even x of n minus 1 will be the previous sample what you will be calculating to update our weights in the future of it along with the current weight. So, next one is the finite precision effects one has to consider. So, what is this? We have seen this effect in case of IR filter, the same thing we will be using it. So, we have assumed the range input is going to be in the range between minus 1 and 1. So, we will be scaling our signal so that the input, if it is a sine wave, the magnitude is going to be between minus 1 and 1. So, any either even the cos function if you have considered, or any speech signal or any audio signal, you will be considering the magnitude to be between minus 1 and 1. So, later on we have to do scaling, finite word effects and arithmetic errors can be considered. So, however, we have done in the case of IR filter. So, we will be taking care of the scaling, and then finite word effects representing our coefficients, even mu has to be approximated after the thing, and then whatever additional what we are doing it, the errors have to be considered. So, we know that E of n, that is feedback for coefficients, scaling is going to be complicated. So, what is it? Earlier in the FIR filter we did not have the feedback. So, you will be seeing in the figure we have a, from the error we are having a feedback path in the thing. So, this also has to be considered. Then what happens? Also the dynamic range of the filter output is determined by the time varying filter coefficients, which are unknown at the design stage. In the FIR filter we have computed our coefficients, and then we knew that what will be the maximum precision what we are going to get it. Here what is the thing is going to happen is, because we are on the go, our weight function is getting updated. So, we say that it is a time varying filter coefficients what we have to calculate, and we do not know at the design stage whether they are going to overflow or underflow, or one has to consider that. So, we say for adaptive FIR filtering with LMS algorithm, the scaling of the filter output and coefficients can be achieved by scaling the desired signal, that is D of n. So, the scaling factor A, which is in between 0 and 1, is used to prevent overflow of the filter coefficients during the coefficient update. So, reducing the magnitude of D of n reduces the gain demand on the filter, thereby reducing the magnitude of the coefficient values. Since A only scales the desired signal, so it is not going to affect the convergence rate, which depends on the magnitude spectrum and power of input signal. So, that is x of n. So, D of n is not going to come into our spectral calculation or power calculation. So, it is not going to degrade our performance when we do the scaling of desired signal. So, y of n minus d of n, so which is going to be kept in not to overflow, fine. So, what will be the thing now, continuing with the finite precision LMS algorithm can be how it is going to be described, that is using the rounding operations. So, we know that y of n is equal to, that is value is going to be rounded. So, here it is not the autocorrelation matrix what we are representing it, it is the rounding. So, the magnitude of whatever the equation we have, FIR filter equation, which is going to be rounded. Then E of n is going to be resulted as rounded off our A times d of n, that is scaling of our desired signal, minus y of n, the magnitude of it will be rounding it. Then what happens to our weight function, updation function. So, that is also going to be rounded, and then you will be having W of n, this equation x of n minus L into E of n. L will be varying between 0 to L minus 1. So, that is what it says is R of x, in this case fixed point rounding of the quantity x. So, when updating coefficients, the product, whatever product we have it, is a double precision number, because E of n is a floating point number, even mu is also going to be floating point, and x of n is also going to be either fixed point or floating point. Still the result of two floating point numbers has to be double precision. If we has used 32 bit for both of them, then it becomes 64 bit, which is double precision number. So, which is added to the original stored weight value W1 of WL of n, and then rounded to obtain the updated value W of L of n plus 1. So, adaptation will stop when this update term is rounded to 0. If its value is smaller than the LSB of the hardware what we consider, this phenomenon is known as stalling or lockup. So, this problem may be solved by using more bits and are using larger step size mu to guarantee that convergence of the algorithm. Okay. However, we know that using a larger step size will increase our x is mean square error. So, the other variant of our LMS algorithm is the leaky LMS algorithm. So, this is defined, that is to reduce numerical errors accumulated in the filter coefficients. So, this algorithm prevents coefficient update overflow from the finite precision implementation by providing a compromise between minimizing the mean square error and constraining the energy of the adaptive filter. So, which is given by expression is given as V times W of n plus mu into x of n into E of n. So, where V is leakage factor, one is going to consider, it is going to be between 0 and 1. So, if it is 1, we know that it is going to be LMS algorithm. So, the leaky LMS algorithm not only prevents unconstrained weight overflow, but also limits the power of output signal y of n in order to avoid nonlinear distortion of the transducers, basically such as loudspeakers driven by the filter output. So, we know that when we are having a speech or audio thing, the output is going to our loudspeakers. So, this distortion is going to be reduced by using our leaky LMS algorithm. The excess power of errors caused by the leakage is proportional to what we call it as 1 minus V whole divided by mu in to the power square. So, 1 minus V should be kept smaller than mu in order to maintain an acceptable level of performance. This is adaptive FIF filter objects. If you refer to the book, here the book is with the reference is going to be given. So, you will be seeing that adaptive field.lms, these are the functions one can use for adaptive filter, that is direct form leaky LMS algorithm. So, different methods have been given. One has to keep it in mind that this adaptive field.lms has been removed in the latest version of MATLAB, that is 2020B. So, you have to use it as DSP.LMS filter. So, and then properly modify the codes, and then you have to use it in your assignments or your work when you want to implement these filters. So, the code what it is given, that is you will be having the random seed, what it is generated, and then you have been given the coefficients of B. So, you will be filtering the signal, and then you are assigning your mu value as 0.05 and then call this function which has to be modified. So, we will see how we are going to modify these to the 2020 B MATLAB and then use this filter to filter the things. So, these are the steps. So, when you observe that this is the desired signal d of n, what it is plotted, and then you will be seeing that error signal which was very high, which is shown in red, which is going to slow down, and then you will be what is it, almost minimized here. So, this is what your output signal y of n is going to look like, and error signal. So, initially you will be seeing that our output signal has little bit of noise and other things. So, when error is minimized, so it will be following the our input signal. So, in the next class we will be seeing our adaptive filter applications. So, thank you for listening to this lecture.